Hi, this is Miguel Zumalacárregui. Welcome to this video introduction to the high class code. And first of all, we'll take a look to the class code on which high class is based. Let us start by taking a look at the website. So the website is in classcode.net here, and in this website you can find all the basic information and links to more detailed information about the code. For example, you can download the code by entering your email address here and then pressing download. This will give you a compressed version of the code that you can expand. Later on we will see that there is a better way to download the code if you use Git, and I would totally recommend to use that. You can also find the information links to all the documentation. For example, the installation wiki page where there are details on how to install the code. For example, in Mac, if you use it, you might need to change a couple things. And also other resources. For example, there is a link to the Class 1 overview paper, which you might want to read to get familiar with the structure of the code, if you haven't done so. Another important thing is that there are also slides from class dedicated courses where you might find more detailed information about the class code and different aspects, how to modify it, the different modules of the code, the principles behind it, and also, very importantly, how to link it to MontePython, which is the Markov chain Monte Carlo extension for class used for parameter extraction. Here you can also find compilation of all the papers in which the different parts of class have been developed, as well as a version history in which the different versions are explained, together with all the modifications that have been implemented. So let's take a look on how to install the code. So the easiest way to download the code would be to enter your email address here and press download. However, I would recommend to use the Git repository in order to have the whole revision control, and this will give you a lot more options to develop and access different versions of the code. So for that, we click on this link here. This will send us directly to the GitHub page for the class public repository. And here, you can also press on the download zip button here in this corner. Or if you have Git, you can copy this link and then opening a terminal window, just use the command git clone and then paste the address. Doing this will automatically create a class public directory and download all the code, including previous versions, into that folder. So this is happening right now. And so now you see I can access this class public directory, and I have here all the files. So then in order to compile the code, I just type make class, and this will run the whole installation process. Okay, so once the code has been compiled, it can be run very easily just by typing class, and then one has to specify an initialization file. So the default initialization file is explanatory, and by running this, the code will take the input from explanatory and then produce the output according to the specifications given. In this case, the output is written in this particular. So the code can also accept as an input an initialization file. That is a requirement that will pass the parameters associated to the computation we want to do. But you can also run with a precision file. So let's see. Let's run with explanatory again. And we can also add a precision file. Precision files have this pre suffix, and they determine how precise or fast the computation will be. So this is a second argument, and it's optional. Let's do this. Chi-square PL 0.01 is means that the precision of the computation will be of 0.01 in the CLs. This will of course require more time, a longer computation than in the previous case default, that is the default, but will be more precise. So now let's take a look at the initialization files. You can see here I've opened in the class public folder I just cloned from GitHub. And you can see that there are several initialization files. There is a concise.ini file that, as the name tells us, it's very simple, and this will be a file that if you run it will pass these options that are very minimal, and all the other parameters will be the default ones. So bear in mind that the initialization files can be as short as you want, as long as you pass all the parameters that you're going to change. However, there is a special initialization file that it's called explanatory.ini. Now, explanatory.ini, it's worth reading, and you should do it, because it contains an almost exhaustive description of all the input parameters and also their compatibilities. It is worth mentioning that in class the parameters are interpreted, and this means that the code will read your parameters and then will infer the basic cosmological parameters that will be used based on your input. For example, here we see that for the baryon density, as it is explained, one can write big omega b or small omega b, which is big omega b times h squared, but not the two of them. So the code will take whichever one you feed, and then use it to compute the the variables inside the code. So you have some redundancy in how you specify the parameters that can be very handy. And of course the code will check that these are the parameters you give are compatible. So you should take a look at this explanatory.ini. It's a very convenient resource to find all the options that you can have. And this goes for the cosmic components, where it's explained where you can have ultra-relativistic species, cold dark matter, decaying cold dark matter, and relativistic decay products, and a long list of possible ingredients, including massive neutrinos or other non-cold dark matters, some simple dark energy models, and lots of other stuff, for example quintessence. There are also parameters associated to the thermodynamics that just go to the thermodynamics module. There are also parameters associated to the perturbations that want to be computed. So, for example, you should specify what spectra you want. If you want CMB temperature, polarization, length CMB, and there are a bunch of other options for the matter power spectra or galaxy number counts. These go into the output flag, the output variable. and so on and so forth. You can take a look at all the other options that you have in class. These are go from methods to compute different things. For example, the tensor perturbations, to the gauge for the perturbations, the primordial initial conditions, and really lots of other things. You have a lot of options that have been implemented in the code, and this should also give you an idea of how flexible and how general class has been made. There are lots of stuff. Let me just jump towards the end. There are some very important flags here that are these verbose parameters right at the very end, and this will control how much information the code gives when you execute it. So if you run, let me change this. If you are having a problem, for example, in the perturbations, you can just change the primordial verbose, sorry, not primordial, perturbations value to 10, from 1 to 10. The higher the value, the more information it will give you. And then if you run explanatory, it will, as it goes through each of the perturbation modes, it will increase a lot the information that you're getting. So if you run into some trouble, it will be easier for you to find out where the problems are. And just a quick word on the format of these initialization files is that you can write whatever you want. You can write comments, you can write any text that you want without giving it as a comment, as long as you don't use the equal sign. So the code class will only read the lines that contain an equal sign, and it will try to interpret those. So be careful if you write equal signs, then you can write them as a comment. So with this hash value, then you can write equal whatever, and then this will not be interpreted. So now let's take a look at the output. So the output, it's all the details about the output are at the end of explanatory.ini, and in particular you will find all the flags that will allow you to determine what you want the code to give you. So a very important one is this root. Here is commented out. Root is used to specify the output directory as well as the name of the file. So the output will be left in the output directory, and then for this run, all the files will be test underscored, and then there will be one file for each type of output. You can configure other options. For example, if you want headers in your files explaining what each column means, the format, etc. And also you can specify what outputs you want. For example, if you want to write the background, we'll have to change this to yes. You can also specify if you want the code to give you perturbations for the evolution of perturbations for several scales. You can also uncomment this line, and then you will have all this. Now we have to save the explanatory.ini, and here we go back to class. We run the code for explanatory.ini, and then the model is compute. Now you see that the output is with the in the directory and with the name that we specified some seconds ago. So we can go to the output directory and see that precisely there are some test underscore and then several files. So one for the background, one for the temperature CLs, and also the other CLs, and lengths as well as lengths. And there are other files. For example, well, as I also asked, there are several files for the perturbations, And then there is an init file with the parameters. You can take a look at that, which you can also use as a parameter file for a further for a future run. This is very useful as a reference because then you can come back and see what exact parameters you used in the model. There is also another file that it's worth noticing, the unused parameters, in which the class will output all the parameters that have not been correctly interpreted. So these are parameters that for some reason have not been used, probably because some of the, even though they're specified, some of the options made that the code did not require them. For example, there are these non-cold dark matter masses that have been read but not used because we didn't ask for any non-cold dark matter in the code, in the initialization file. So this is useful to look at if you think that the code is doing something funny. So let's take a look at the first output, is the background. So we can look at the file, and well, the first thing that you'll see is the header with some comments, and here you can see all the columns that you have. These headers are very useful because they contain the information you need to understand all your output. So for example, here the units are specified, so all densities are in units of h pi j3, so that the equation, the Friedman equation, is just h squared equal density, and the densities are in order corresponding units of megaparsec to the -2, while all distances are megaparsecs. This is also explained in each column. It's further specified. So let's say we want to plot the Hubble scale as a function of redshift. So these are columns 1 and 4, and we could go to GnuPlot and then plot test background using columns 1 and 4, and this gives us a plot of the Hubble rate as a function of the redshift. Now this plot is unfortunately not very meaningful, so let's set a logarithmic scale and do the plot again. Now this is more like it. And likewise, you can plot any other thing that you want. You can look at the output of test CLs, for example, where you can see the conventions we're using. So these are dimensionless total CLs. The input output, it even gives you some suggestions on the format and how you can change it. And you can see what each column means. So let's plot the temperature spectrum, for example. So this would be plot test CL dot dat using 1 and 2, and this will give us the temperature spectrum for the model under consideration. One can also take a look at other files. For example, the perturbations test perturbations k. There are different modes. So let's look at k0.dat. So the header immediately tells us that's the evolution of scalar perturbations for a mode with k equal to 1 times 10 to the -4 inverse megaparsecs. And you can see that the column means so the conformal time, the scale factor, and then the evolution of the different variables. So let's, for example, look at the gravitational potential psi. So that's the column 11 as a function of the scale factor. So that would be plot test perturbations k0.s.dat using 1 and 11. This gives us this, and not so exciting, but then let's add another k mode. So K1, that's another, corresponds to another scale, time 11. And you can see that the evolution is different. Now we've asked the code to give us 3 modes, so then we can go for perturbations K2 and plot the same. So this gives us 4 different scales. You can see that, for example, in this K2, that's the smaller scale that crosses the horizon early, and it undergoes some baryon acoustic oscillation. So it's a mode that enters the horizon before recombination. As you can see, all of this is very useful to compute models, and you can use the output directly to understand the physics associated to this, to each of the models that you get the output for. So let's just finish up by pointing out 2 other resources that you will have at your disposal as a class user. So first of all, didn't mention this before, but class is based entirely on the paper, a very famous paper by Ma and Bertschinger on cosmological perturbation theory. So in particular, all the equations in the paper, all the notation, all the conventions are as in this very well-known review or adapted from this review. For example, Julien Lesgourgs and Thomas Tram adapted the formalism of Ma and Bertschinger to non-flat spacetimes. So if you have any doubts about the notation, you can always find this very good classical reference and use it as a guidance. Now, I mentioned before that there are class courses with a lot of slides and information on how to understand the code and various technical details. These slides, very importantly, also have exercises that you can complete, and they will give you a lot of familiarity with the code and even help you understand on how to do some small modifications that will be useful if you want to use the code for models that have not yet been implemented. Now the GitHub, another important resource is the GitHub page, because the GitHub page contains all the previous versions of the code. So for example, you can go here to graphs and network, and this will give you an idea of how different users have contributed different implementations of all the features. So here from this page, you can just click on one point. Each point represents a set of changes, and you can see all the things that have been modified with respect to previous versions. So besides having all the previous versions in GitHub, you also have other useful tools. For example, there is a wiki where you can find some of the documentation and frequently asked questions, details on the installation of the code, and other aspects. And very importantly, there is another tab that's called Issues, where you can find all the problems people have had with the code. So this is a living community. You can find problems that people have filed, and problems that are yet to be solved, and problems that have been solved already. So if you have any difficulty with the code, this is a very good place to look at. So you can check if your problem you are experiencing has been reported, and in which case there might be a solution already. And if you detect a bug on the code or a problem with your operating system or something else that is not working as you would expect it, you can file it here as a new issue, and then the whole class community will contribute to, will be able to help you and fix the bug or give you ideas on how to solve this particular problem. So I hope this has given you an idea of the class code. There are, of course, lots of resources. I really recommend you to check the courses and do the exercises. And you can of course email me if there are specific questions that you have.